Welcome back, students. In this lecture, we will see an example on how to analyze an indeterminate structure having support settlement using moment distribution method. Okay, without delay, let's get into the problem. So here we have a two-span bridge ABC, each of span 8 meters. The loading on the first span AB is a center point load 20 kN. Loading on the second span is BC is a 3 kN UDL throughout. The first span is having an flexure rigidity of 2EI, second span is having flexure rigidity of 3EI, and there is also some joint moments applied at joint A and joint B. At joint A we have a clockwise 12 kN and joint B we have anti-clockwise 15 kN. Okay. It is also given that importantly the support B settles down by 10 millimeters. Okay. So there is a delta value here which is 10 millimeter, which is 10 into 10 raised to minus 3 meters. Okay, EI value is also given, so you can find out what is the EI value and substitute the value here. So we have got only one internal hinge, sorry, internal support. So first step is you have to find out the distribution factor. So support A is a simple joint, which means that distribution factors DFAB is going to be 1. Support C is a fixed support, which means that DFCB is going to be 0. The remaining is DFBA and DFBC. So consider joint B. So when we consider joint B, the far end for span BA is simply supported and far end for joint BC is fixed support. So DFBA is equal to, it is far end is simply supported, so 3 into EI value, which is 2EI, divided by span length, which is 8. Okay, for the second span BC, DFBC is equal to, far end is fixed, so 4EI, so 4 into EI is 3EI divided by L, which is 8 meters. So these are the two K. This is the K value for first span. This is the stiffness of span BA. This is stiffness of span BC. So you can find DFBA as 3 into 2A by 8 divided by 3 into 2A by 8 plus 4 into 3A by 8. So you get 0.333 as DFBA. Sum of distribution factor at a particular internal joint is always equal to 1, which means that DFBC can be found at either 1 minus DFB, which is 0.667. Okay. So you got the value of DFBC as well. Next step is important, like at this particular point problem we have got a support settlement. So when you're finding out the fixed moments, you have to consider this support settlement as well. Okay, that is the only difference which is going to be happening here. So normally we have for span AB we have a center point loads 20, so we will have take PL by 8. For that substitute P is equal to 20 and L is equal to span is equal to 8. So FEM due to point load is 20 kN. You have to consider the sign convention later. And FEM due to UDL is WL square by 12 in the second span. So W is 3, L is 8. Substituting we have 16 kN FEM due to UDL as well. Okay. Next part is we have to find out what is the value of fixed moment when you have a support settlement. So B subtends by 10 meter downward. So the settlement is something like this. Okay, this is settlement as well as this is the pattern of settlement. So this particular settlement is called as delta. Okay, and it is given as 10 millimeters, 0.01 meters. Okay, so fixed moment for support settlement is given here. So whenever support settlements happen and the beam rotates as a whole in clockwise direction, okay, as in the case for the span AB, as a whole the beam is rotating in the clockwise direction. So the fixed moment developed at A and B will be in the anti-clockwise direction. So you can see MA is anti-clockwise, MB is also anti-clockwise. and the value is going to be 6ei delta by L square. Here also value is going to be 6ei delta by L square. Clear? So if you consider the sign convention RAN, reactive anticlockwise moments are negative. So we have both FEMs as anticlockwise, which means that both the FEM value 6a delta by L square is going to be negative. So FEM AB and FEM BA due to delta is going to be negative. So FEM AB is going to be having a minus 6a by delta L square. Similarly, FEM BA is also going to have a minus 6a delta by L square. Okay, and FEM AB, the contribution of point load in FEM AB is also minus, because on the left hand side we have a anti-clockwise moment and due to FEM from point load, and point load causes a clockwise FEM on the right hand side. So FEM BA is equal to plus CPL by 8. Okay, so for the second span BC, it is important to note that the beam rotates as a whole in the anti-clockwise direction. So beam is rotating something like this. Delta is here, so this is the span point B, this is the point C. The beam rotates as a whole in the anti-clockwise direction, which means that the moment at fixed moment at B and fixed moment at C is going to be clockwise direction. So it is going to be in clockwise direction. FEM here also, FEM is going to be in clockwise direction. Okay, which means that these reactive moments are clockwise, which means that it is positive in value. So FEM BC due to delta is positive. Similarly, FEM CB due to delta is also positive. FEM due to W at B is going to be negative, and FEM due to UDL at C is going to be positive, because on right hand side we have a clockwise FEM value and on the left hand side we have a anti-clockwise value. So once we find out the FEM values, you have to list down all the values, substitute all the values and find out the FEM. You have to draw the moment distribution table. So normally you start up with listing out the distribution factor values DF. So it's the right hand side, which is C, it is a fixed one, fixed joint, so distribution factor is 0. The symbol end A is symbol end, so distribution factor is 1. Okay, we also got some moments, so active anti-clockwise moments are positive, right? So let's see whether there are any active anti-clockwise moments. Yes, so we have an 15 kilonewton active anti-clockwise moment, so that is a positive moment as far as the sign convention is considered. So this particular thing has to be negated, so minus 15 is to be applied at B. However, it has to be distributed among the span BA and BC. So minus 15 multiplied by 0.33, that is going to be minus 5 here, and minus 15 multiplied by 0.667, this is going to be minus 10 here, right? Similarly, there is a clockwise moment, active clockwise moment of 12, which means that that is negative moment. So in order to balance it, we have to apply a plus 12 multiplied by DF, which is 1. So we have a plus 12 applied here at A. Okay. There is no requirement of distribution because there is only one member meeting at A, right? So once we do that, you have to notice that for this 12, the far end B is fixed, so half of 12 has to be carried over to here. So 12 by 2, 6 is carried over with same sign. For this particular minus 5, the far end is symbol end, which means that there is no carryover. The carryover value is 0. Okay. For this moment minus 10, the far end is C, which is fixed, which means that half of this minus 10 is carried over to C. So we have minus 5. Okay, so that is the carryover step. The next step is you have to write down all the fixed moments you have found out with the sign convention, proper sign convention. So once we do that, then that step is over. Next step is you have to release the simple end. So at simple end there was a fixed moment of minus 38.75. So in order to release that, we apply a plus 38.75 at A, and since the far end B is an internal joint which is treated as a fixed support, half of 38.75 is carried over and it is given at B. So 19.375 is given at B. So next up what you have to do is you have to sum these three columns from starting from carryover up to the release. These three columns has to be summed up and you have to write down these initial moments. Okay, so once you get the initial moments, the remaining step is you have to do the proper distribution, moment distribution. So at B we have a total positive value of around 38.75, right? So plus 38.75 is there, so in order to balance that we have to give a negative 38.75 and it is to be distributed among B, A and BC. So minus 38.75 multiplied by 0.33, that will come here. Minus 13.75 multiplied by 0.667, that will come here. Okay, that is an unbalanced moment of 39.125 at C. However, the distribution factor is 0 at C, which means that the distribution value is 0. Okay, for this particular joint value minus 12.904, the far end is A, which is simple support, so carryover is 0. For this particular minus 25, the far end is C, which means that there is a carryover of half the moment, so minus 25.834 divided by 2 minus 12.917. This is 0 is half of 0 has to be carried over to here, which will be again 0. Okay, at this point when we consider all the carryovers, there is only one unbalanced moment at C. So minus 12.917 is an unbalanced moment at C. Multiplied with distribution factor 0, you have distribution as 0. So with this you can stop your moment distribution. So next step is you have to sum up all the values from starting from initial moment up to the distribution. So all these four values has to be summed up along with the first joint distribution moments. So 12 plus 0 plus 0. So from here the first line joint coupled moment distribution plus this initial moments up to distribution, this has to be summed up. So 12 plus 0 plus 0, the value is plus 12, minus 5 plus 26.625 minus 12.904, you get plus 8.721, minus 10 plus 12.125 minus 25.834, you get minus 23.709, 0 plus 39.125 plus 0 minus 12.917, you get plus 26.208. So once you get all the moments, you can mark out your active moments in the beam. So you will use again the same sign convention. Active anti-clockwise moments are positive, so there is a positive moment here, which means that support moment at A is going to be anti-clockwise. So this is your support moment. Again here it is a plus 26.8 point plus 8.721, you can mark that here. Active anti-clockwise moments are positive, anti-clockwise here, and this is going to be clockwise, right? This is again going to be anti-clockwise because it is a positive moment. So finally you can find out the reaction values and also obtain the bending moment diagram, right? So the final bending moment diagram will look something like this. Okay, so thank you, that's it for today's lecture.